So as we mentioned here, if you have two groups around the central atom, hybridization is sp. Three groups hybridization is sp2, and four groups hybridization is sp3. So showing hybridization and bonding in alkanes. Alkanes are hydrocarbons that are made up of carbon single bond carbon. So if you have a carbon single bond carbon over there, this is the simplest, which is ethane. It is the simplest. If I want to count my sigma bonds are going to be, now I know that each of these carbon is going to be tetrahedral, and each of these carbons is going to be an sp3 hybridization. So this carbon is an sp3, and this carbon is going to be an sp3 hybridization. So if it's an sp3 hybridization, then these are my four groups around it. Each one is going to be an sp3 hybrid orbital. So I have an sp3 hybrid orbital here, 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 and here. And the sp3 hybrid orbital is going to overlap with these three hydrogens on this side. So with the 1s, this is the s orbital of the hydrogen. This is the hybrid orbital there of the carbon. This is the 1s of the hydrogen and the hybrid orbital of the carbon, the 1s orbital of the hydrogen and the hybrid orbital of the carbon. Probably the hybrid orbital is not shown. To make those three sigma bonds in here, I have another sigma bond where the two sp3px orbitals, these are the sp3px orbitals, they overlap in there in order to form my sigma bond. So these two sp3 orbitals, they overlap, they form a carbon-carbon single bond. So each carbon has 4 sp3 hybrid orbital, 4 sp3 hybrid orbital. So the total number of sigma bonds is going to be over here 3, 4, 5, 6, and 7. With respect to alkenes, alkenes basically have a sigma bond here, a sigma bond, a sigma bond, a sigma and a sigma. So they have 5 sigma bonds, and see that double bond in there, this bond, this is going to be a pi bond. So let's explain. If you look at the hybridization of these two carbons in here, so the hybridization, because both are going to be the central atoms, so the hybridization of this carbon has 3 groups around it, right? So it is an sp2 hybridization. It is planar, it's a trigonal planar with 120-degree bond angle. And this carbon is the same, having an sp2 hybridization. So if you do the hybridization, if you do the excitation, you hybridize. What I need is just the 3 groups. I don't need 4 groups because I don't have 4 groups. I only need the 3 groups in there. So only the 3 orbitals in there that are gonna hybridize. This is the hybridization orbitals that I need. There will be one left over p orbital that I don't want it to hybridize because I don't need it to hybridize. So that p orbital for one carbon is going to overlap with the another 2p orbital of the other carbon and basically make a pi bond. The p orbital has a shape of a dumbbell. The sp2 orbital has a shape of basically a lobe like this. My drawing is a little bit funky. So here you go. My sp2 has basically a shape of a big lobe and a small lobe in here. So this is the same shape as the sp3. The hybrid orbitals have basically the same shape, but normally I can use the hybrid orbitals as I need. Here I only need 1, 2, 3 hybrid orbitals. I don't need 4 because I have 3 groups around the carbon. So you choose the 3 hybrid orbital and you leave 1 orbital non-hybridized. That is going to remain in the form of 2p. A pi orbital is the overlap of p orbitals. When you have 2p orbitals overlapping with each other, this means that you are going to form a double bond. So this is the valence bond representation. An alkene is going to have, so ethene in this case has the following. It has a sigma bond. It has a sigma bond here. This is the overlap. This is the sp3 or sp2, I'm sorry. Hybrid orbital of the carbon with the 1s of the hydrogen. This is the sp2 hybrid orbital of the carbon with the 1s of the hydrogen. And this is the sp2 hybrid of the carbon, hybrid orbital of the carbon, with the other sp2 hybrid orbital of the carbon. So each one has one electron. They overlap to make 2 electrons here, 2 electrons here, 2 electrons in there. And in that case, we're going to form our sigma bond. So you have a sigma bond, sigma bond, sigma bond. Here you do the same thing. This is the sp2 hybrid orbital. This is the sp2 hybrid orbital that overlaps with the 1s hydrogen orbital. So the total number of sigma bonds is going to be 5. Now with respect to the pi bonds, the pi bonds is the overlap of the p orbitals. So this carbon is going to have a p orbital with 1 electron. Why it is 1 electron? Let me go back. Because it is 1 electron over here. Remember when we did hybridization? When we did the hybridization, this electron got excited to the p orbital. But I only needed 3 of them. I only needed 3 orbitals to hybridize because I have 3 groups around the carbon. So I'm going to leave the p orbital non-hybridized in a form of p orbital in there. So to draw the p orbital, just show it as 2 lobes. And there this is a dumbbell shape. And the p orbital has 1 electron for one carbon, 1 electron for the other. When the p orbitals overlap, they make a pi bond. Now for the triple bond, we're going to do the same thing. We're going to hybridize, so you're going to hybridize in there. So this electron is going to get excited to the 2p orbital, but I only need 2 orbitals because I have 2 groups around the central atom. So needing 2 orbitals in there, I only need these 2 orbitals to hybridize. This is going to leave these 2 p orbitals there, the py and the pz. Okay, these 2p orbitals are going to be left for each carbon. So this carbon 1 is going to have py, pz. Carbon 2 is going to have again py and pz. The py's will overlap together to make a pi bond. The pz's will overlap together to make another pi bond. So basically here, this bond is going to be the sigma bond, which is the overlap of the 2 sp hybrid orbitals of the carbon. And then those 2 double bonds in there, these are 2 pi bonds. And these 2 pi bonds are the overlap of the p orbitals. So if you have the pi y of one carbon, or the py of one carbon overlapping with the py of the other carbon, then you're going to have the pi 1. This is the first double bond. And if you have the pz, where is my pz over there? If you have the pz is going to overlap with the other pz there. Okay, and it's going to make the pi 2. That is going to basically make the pi 2 hybrid orbital, or the pi 2 double bond in there. So the triple bond has 2 pi bonds, and it has, let's count the sigma bonds. The sigma bond representation has 1 sigma here, 1 sigma here, and 1 sigma here. And the sigma is the overlap of the s orbital with the sp hybrid orbital of the carbon, 2 sp hybrid orbitals of the carbon, and the sp and the s orbital of the hydrogen. So you have 3 sigma bonds in this case. Normally when we represent the valence bond representation, we separate the double bonds from triple bonds just to avoid the clutter in the graph. Though we don't show the double bonds, the triple bonds, or the sigma and the pi bonds all together. We show the sigma alone and the pi alone. So the idea is, if you have 4 groups bonded to the carbon, then the hybridization is sp3, bond angle is 109.5, and you will be forming sigma bonds. All of these sigma bonds, they are an overlap of sp3 1s orbital sigma bonds for the hydrogens, and carbon sp3 between the carbons. If you have 3 groups bonded to the carbon, then the hybridization is sp2, because you would need 3 orbitals in this case. So the number of groups around the central atom, this is the same as the number of orbitals needed, and this is how you get your hybridization. And the hybridization explains how sigma and pi bonds are formed. So in that case, I would have All of these bonds are going to be the sigma bonds, that they are the overlap. Now between the two carbons is going to be the overlap between carbon sp2, carbon sp2. Between the carbon hydrogen is going to be the overlap between carbon sp2 and hydrogen 1s. And then for the pi bond, is the overlap of the two p orbitals. Both have two p orbitals having one electron in each. And same explanation as groups bonded to the two groups bonded to the carbon, then the hybridization is sp, the bond angle is 180, and then you're going to end up having two p orbitals, and basically you're going to end up having a sigma bond that is an overlap between the two carbons in there, the two sp hybrid orbitals of the carbon, another sigma bond between the sp carbon and the hydrogen 1s, and here the sp carbon and the hydrogen 1s. This is figuring the hybridization as I mentioned. So you look at the central atom. Always look at the central atom because hybridization is the central atom. Figure out how many groups are connected to the central. So here I have water again. I have two lone pairs. You don't do hybridization before drawing the Lewis structure and figuring out how many lone pairs you have on the central. Once you do this, then you go ahead and figure out the hybridization of the central atom. I have four groups around the central atom. So each of these are going to be on the sp3 hybrid orbital. So this means, see those lone pairs? They belong, each one of them, to the sp3 hybrid orbital. So you draw one in the sp3 hybrid orbital and another one in the sp3 hybrid orbital like I'm drawing over here. Same thing for the NH3. Okay? What orbitals are used to form each bond in methanol? Again, carbon. Carbon over here is surrounded by four groups, so it's an sp3 hybridization. Oxygen, four groups, it's an sp3 hybridization. To form a bond between the carbon and the hydrogen, I need the sp3 hybrid orbital of the carbon. This is going to overlap with the ns orbital of the hydrogen. To form the CO bond, I need the sp3 hybrid orbital of the carbon to overlap with the sp3 hybrid orbital of the oxygen. And to form a bond between the O and the H, I need an sp3 hybrid orbital of the oxygen to overlap with the 1s of the hydrogen. Same idea over here, determine the hybridization. This carbon has four groups, it's an sp3 hybridization. This carbon has three groups, it's an sp2 hybridization. This oxygen over here has 1, 2, 3 groups, and it is an sp2 hybridization. One thing that I want to say, if you have a double bond, always the hybridization of atoms around the double bond is sp2. If you have a triple bond, then if you have a triple bond like that, then the hybridization around the triple bond is an sp. Okay, and if you have a single bond, then the hybridization is going to be sp3, but it depends if you have a lone pair or not. So you can easily figure out the answer over here. Determine the hybridization of each of the highlighted atoms. So you look at this carbon. It has 3 bonds and a bond. Carbon makes 4 bonds. So this carbon over here is an sp3 hybridization. This carbon here has 2 groups, so it's an sp. So again, carbons around the triple bond, they have an sp hybridization because you have 2 groups around the carbon. Now this nitrogen, it does have 1, 2, 3 groups, so it is an sp2 hybridization. And again, groups around the double bond should always have an sp2 hybridization. They are planar, bond angle 120 degrees. This carbon over here has a 3, 4, so it is an sp3 hybridization. I need 4 orbitals there. And this carbon has 1, 2, 3 groups. So again, it is an sp2 hybridization. So again, carbons or any groups around the double bonds, they should have an sp2 hybridization. So this here is going to be an sp2, right? And this carbon over here, it's going to be two groups. This is a CH2, so you have two hydrogens there, two groups, and this is a 3, so it's an sp2 hybridization. Now what about this carbon? Is it an sp2? Well, not actually, because this carbon has two bonds around it, or two groups around it, so I only need two orbitals, and this is an sp hybridization. Find out the hybridization for each one of those. I would like you to do them. I will include the answer in the PowerPoint. Same thing for this one over here. So the hybridization of this carbon, I do have two hydrogens over here. This is a skeletal form. So it's 1, 2, 3, 4 groups. So it's an sp3 hybridization. For this nitrogen, well, I need to draw the Lewis structure, as I mentioned. Never, ever, ever do the hybridization before you draw the Lewis structure. So drawing the Lewis structure is going to tell you that you have two lone pairs in there with a negative charge. So now I can easily determine my hybridization 1, 2, 3, and 4 groups. Then it's an sp3 on the nitrogen. On this carbon over here, this is a hydrogen. It's 1, 2, 3 groups. This is 1, 2, and 3 groups. So I need the 3 orbitals. It's an sp2. Remember what I said. Around the double bonds, it's always sp2. Unless you have two double bonds next to each other, then it has to be like in this example over here. Then one of them is going to be an sp. It cannot be sp2 both. So this carbon over here, this is 1, 2, and 3 groups. So it is an sp2 hybridization. And this nitrogen over here, it's not a drawn. The Lewis structure is not drawn. See, it's a drawn over here, but it's not drawn there. So I have to show the lone pairs on the nitrogen, because I know that nitrogen has 3 bonds and a lone pair to be a 0 charge. I already have it 0 charge, so I know that I am missing a lone pair. So here you go, around the nitrogen I have 1, 2, 3, and 4 groups. So since I have 4 groups in there, then that is going to be an sp3 hybridization on the nitrogen. Okay. For intermediates. Now in organic we're going to pass by different intermediates. And these intermediates are completely unstable. They are basically carbons with charges or carbons with neutral charge. There is no charge in there. So if you have a carbon that has a positive charge, what is that? A carbon that has a positive charge is basically a carbon that has an empty p orbital. Why I am saying an empty p orbital? So I'm looking at the carbocation in here. What's the hybridization of this carbon? The hybridization of this carbon has 3 bonds, right? So the hybridization is sp2. When you do an sp2 hybridization, you're going to be left with 1 p orbital. That p orbital, because it has a plus charge, that p orbital is empty. I said that you're going to be left with 1 p orbital because remember that you have 4 orbitals in there. So if you use 3 of them, you're going to be left with 1. If you use 2 of them, you're going to be left with 2. Pay attention to that. Okay? So that p orbital is empty. So normally what we do, we draw it as a p orbital and we draw it as an empty in there. There is no charge, nothing in there. A plus in it means it's an empty p orbital. But the hybridization of this carbon is sp2. Now what about the carbon ion? The carbon ion in here has 3 bonds and a lone pair. So I want to figure out where the lone pair is. The lone pair is considered to be a group. So this group over here is considered to be with the hybridization. So that's going to be 1, 2, 3, and 4. 4 groups, 4 orbitals. This is the max. So this carbon is going to be sp3. So the lone pair, see, they reside in the sp3 hybrid orbital. If you have a carbon that has 2 bonds and a lone pair, this is completely unstable. This is called a carbene. Now in this slide, what I am up to here is showing you all the unstable intermediates that normally we go with when we do any organic reaction. We might go into a carbon positive charge, carbocations or carbon ions or even carbenes or methyl radicals. All of these, they are unstable intermediates. You have to know their hybridization. So for the carbene, I just want to know where this lone pair resides, because it makes a difference if the lone pair is in the p orbital or if the lone pair is in the hybrid orbital. If the lone pair is in the hybrid orbital, it is locked. I cannot do any resonance, so no resonance with lone pairs in the hybrid orbital. So see, lone pairs in the hybrid orbital cannot have any resonance in there. But lone pairs in the p orbital, they do, because resonance is basically when electrons hop from one p orbital to the other. So with the carbene over here, what I have is 2 bonds and the lone pair. Carbon here is not octet. It has 6 electrons. It's completely unstable. What's the hybridization? The hybridization here, I have 3 groups. So if I have 3 groups, then the lone pair is going to belong to the hybrid orbital. Then I'm going to have an empty p orbital on the carbon. With respect to the methyl radical, I have all of these. I have 3 groups around the central atom. Now the radical, I don't consider it as a group, because it is not a lone pair. I don't consider it as a group at all. So the radical here is going to reside in the p orbital. So the hybridization of this carbon now is an sp2. Okay, this section is just the revision of 115. In this section, we're going to see the difference between ionic and covalent bonds. Ionic bonds are stronger than covalent bonds, way stronger than covalent bonds. Ionic bonds form between groups 1, 2, 3. So groups 1, 2, 3 in the periodic table, and the groups 5, 6, and 7. So like for example, I have sodium in a group 1, fluorine is in a group 7. They form ionic bond. Ionic bond results from the transfer of electrons from one element to the other. So here, as you can see, 1 electron from the sodium. Why 1 electron? Because sodium is in a group 1, it has 1 valence electron. Fluorine is in a group 9, it has 9 valence electrons. So fluorine here, 7. Fluorine is in a group 7, it has 7 valence electrons. So fluorine is not octet yet, but if I transfer 1 electron from the sodium to the fluorine, then fluorine is going to be octet. Sodium will lose a charge, so it will become ionic. It's going to be Na plus, F minus in there. Ionic bonds normally, they form if the difference in electronegativity between the atoms is greater or equal to 1.9. There is an electronegativity table that I'm going to show, and in this electronegativity table you can calculate the electronegativity basically of the bond that you're forming, and if the electronegativity is greater or equal to 1.9, then the bond is ionic. Or you can go with this rule which says that ionic bonds are formed between groups 1, 2, 3, and 5, 6, and 7. When you represent an ionic bond is an ionic interaction. So under no circumstances you're going to draw an actual bond. It's not a true. It's basically an ionic interaction between a plus part of the molecule and a negative charge part of the molecule. So to represent an ionic bond, you represent it as a cation first and then the anion. And of course you need to show the lone pairs in there. Okay, same thing over here. You have to show the lone pairs in there. So chlorine has 8 lone pairs in that case. You don't show a bond between the sodium and the chlorine. With respect to covalent bonds, these are strong bonds, but not stronger than ionic. Ionic are stronger interactions. Ionic bonds, they are not actual bonds. They are interactions, and they are really very strong. Now, for covalent bonds, they result from sharing electrons between the 2 nuclei. So over here, if I want to explain how hydrogen atom is formed, hydrogen diatom is formed. Hydrogen diatom is formed by overlap of the 1s orbital of the hydrogen with the 1s orbital of the hydrogen. These two, they overlap with each other. So notice the electrons are shared. Nothing is transferred. The electrons are shared. So you're sharing an electron and you are making you're making a bond, a 2-electron bond in this case. Normally, covalent bonds are formed between hydrogens and carbons, between diatoms, between oxygens and hydrogens, between nitrogens and hydrogens. So hydrogen should be present in there for a covalent bond. Every time you see a hydrogen, hydrogen makes covalent bonds. Hydrogen can also make ionic bonds, but we're not going to discuss this right now until we reach it. But hydrogens, in most of the cases, they make ionic covalent bonds with carbons, with oxygens, and with nitrogens, and with halogens. So in order to determine if you have an ionic bond or a covalent bond, you look at this chart over here. In the slide after this, I'm going to show you the electronegativity table of how to get these values. So if your electronegativity between the two atoms is greater than 1.9, then the type of bond is an ionic bond. If it is 0.5 to 1.9, then it is a covalent bond, but there is a difference between a polar covalent bond and a non-polar covalent bond. A polar covalent bond means that the electrons basically have a direction, and their direction is towards the more electronegative element. So this is what a polar covalent bond is. The electrons, they move towards the more electronegative element. A non-polar covalent bond means that the electrons, they don't move, they just stay stable and they stay in their place. There is no electronegative element in there. So this is a non-polar covalent bond. Like for example, a carbon single bond carbon. This carbon single bond carbon in here, this is a non-polar covalent bond. Why? Because carbons are basically non-polar. Carbons here, in this case, they are non-polar, so they are not electronegative. So the electronegativity here in this case is going to be less than 0.5. Now, in our case here, because carbons, they do have the same electronegativity, the difference in the electronegativity is going to be 0. So when I say less than 0.5, I include 0 in there. So if it is 0, then it is non-polar covalent. This is the electronegativity table that I'm talking about. You are not required to know to memorize anything. This electronegativity table, you can have it in the exam, and I'm going to provide it in the exam. Okay, so it shows the electronegativity of some of the atoms. As you can see here, carbon is slightly more electronegative than hydrogen, slightly, not too much. And electronegativity increases as I go from left to right in a period and from bottom to top in a group. So fluorine is going to be the most electronegative, iodine is going to be the least electronegative there. The electronegativity includes the direction of polarity. It's the direction how electrons are moving. So if you have a carbon and an oxygen in there, you can see that oxygen is more electronegative than carbon. Then the direction of the movement of electrons is going to be from the carbon to the oxygen. So the carbon is going to lose electrons and it's going to become partial positive. Oxygen is going to gain electrons, it's going to become partial negative. This is called the direction of polarization. It's the direction of the movement of electrons. It's as if oxygen, because it's more electronegative, it's stealing electrons away from the carbon. See, this is the direction of electrons in there. So we're going to say that this bond is a polar bond because the electrons are moving from the carbon to the oxygen. Okay, so this is an example of non-polar bonds when they have electronegativity basically which is less than 0.5. So an electronegativity value which is less than 0.50 or less than 0.5, it really doesn't matter. As long as it's less than 0.5, then we can say that the bond is non-polar. So if you have a CH bond, hydrogen has a 2.2 electronegativity, carbon a 2.5. I'm just reading them from the table before. Subtract them from each other in absolute value. No negative value, okay? So subtract them in absolute value and see if the value is less than 0.5, then this is going to be a nonpolar covalent bond. Now, with respect to nonpolar bonds, these are carbon-carbon bonds. They are nonpolar bonds. Carbon-hydrogen bonds are also nonpolar bonds. And if you have atoms that are the same, for example, H2, O2, N2, so all of those are considered to be nonpolar covalent bonds. Whenever you have two atoms that are the same, with similar electronegativity, then the bond is going to be nonpolar. So over here, N2, so if I am doing N2, this is the Lewis structure for N2. This is nonpolar because both have the same electronegativity. The difference is going to be 0. If you have O2, so if you have oxygen in there, this is the O, this is the O, so I'm having basically, this is the Lewis structure for O2. Again, both are going to be, this is going to be a non-polar covalent bond. So this is going to be a covalent bond. This is going to be a covalent bond in there. Talking about the sigma bonds are covalent bonds. Now, with respect to the polar bonds, you need to have a difference in electronegativity, as I mentioned before. Like the CO, oxygen is more electronegative. So if oxygen is more electronegative, it's going to pull electrons towards itself, stealing electrons from the carbon. To represent a carbon that lacks electrons, we do a partial positive charge. To represent an oxygen that gained electrons from the carbon, we do a partial negative charge. This arrow here is called the direction of polarization, and it shows how electrons are moving across the molecule. If electrons have a direction and they are moving, we call the bond polar. If the electrons are not, so if arrows cancel out, if electrons stop moving, then we say that the bond is basically nonpolar. So let's have an example over here. If I am having a CH3Cl, never ever do polarity, never ever check polarity before you do the following. First, you need to draw the Lewis structure. Second, you need to draw the molecular shape. So molecular shape or geometry, it doesn't matter, but I am saying shape in case there are lone pairs in there, just to take into consideration the lone pairs. After you draw the Lewis structure and the molecular shape, then you are good in order to determine the polarity. You cannot determine the polarity before drawing the molecular shape. So not just from the Lewis structure, you have to draw the shape. See, here I'm drawing the shape of CH3Cl. By the way, I can put the Cl anywhere, but I chose to put the Cl on the planar bond because it is the unique element and it's easier for me if I do this, so that to figure the direction of polarization. Now I know that all of these CH bonds, these are nonpolar because they do have they do have an electronegativity value which is less than 0.5. So all of those are nonpolar, but still carbon is slightly more polar than hydrogen. So the direction of polarization basically is from the hydrogen to the carbon, from the hydrogen to the carbon, from the hydrogen to the carbon in there. It's going to continue because chlorine is electronegative. So chlorine here has a lot of electrons. It is electronegative. See how the electronic map showing a red region around the chlorine. That red region indicates that chlorine is basically rich with electrons. So chlorine is going to steal electrons away from the carbon, and it's going to make this carbon partial positive. This is partial positive and this is partial negative. See how my direction of the arrows is going. It's going up. It's not canceling. So since my direction of polarization or the direction of electrons is going up, then I would say that the molecule is polar because it is not canceling. It does have a direction in there. Now let's have another example. With all of those, draw the Lewis structure and the molecular geometry as I am doing, or shape as I am doing over here. Now determine if the molecule is polar. You have a direction of polarization, the molecule is polar here. Between boron and fluorine, fluorine is more electronegative, so you have two arrows pointing down. The resultant of these two arrows is going to be pointed down. Okay? You have electrons going down, or a force pulling the electrons down, and that same force is pulling the electrons up. So these two arrows are going to cancel out. So we're going to say there is no dipole moment. The molecule is going to be nonpolar. With these two have a resultant coming up. These two vectors have a resultant coming up. So your net dipole is basically coming up. If it's coming up, then the molecule is going to be polar. Same thing over here, your net dipole. Your net dipole, you have these two are not in the same plane to cancel out. Pay attention. So these two chlorines are not in the same plane. These two are, but these two are not. So they cannot cancel out. So you have a direction of polarization going this way, direction of polarization going this way. So the net dipole is going to go that way. And these two polar bonds in there, they're not going to cancel their net dipole. So the molecule is going to be polar. With these two, it's going to cancel because these two have a resultant going down. These two have a resultant basically going down, and then you have the same elements. These are all the chlorines in there, so these two vectors basically are going to cancel out. Or you can do it like this. The net dipole of these two goes this way. The net dipole of these two goes this way. It's equal forces, is the same force pulling opposite ways. So the net dipole is going to cancel out. So the molecule is going to be nonpolar. Let's have an example over here. So which of the following molecules is polar? CH3, Br, it is. Because if you draw it over there, it's the same thing as a CH3Cl as the one that we drew before. So you have your bromine in here. Draw always, as I mentioned, draw always the molecular shape. Please draw the molecular shape in there. So all of those are non-polar, but this CBr bond is basically polar, so it makes the molecule polar. CH2Br2, so let's draw it over here. It's the same thing as the CH2Cl2, exactly the same thing. The molecule will be polar, so you have a bromine here, you have a bromine there, and then you have a hydrogen, and then you have a hydrogen here. So these two are going to be nonpolar, but the CBr and the CBr here, they have a resultant going this way. So the molecule is polar. CF4. CF4 is the same thing as CCl4. The molecule is nonpolar. With respect to this alkene, it's already drawn in the form of the Lewis structure. So let's go ahead and figure it out if it's polar or not. Okay, so this is it. So you have these bonds are not polar. The CH bonds are non-polar. So what I have here is the pull between the carbon and the chlorine and the carbon and the chlorine. So the resultant basically is going up. So the molecule is polar. Here, I am having a pull carbon chlorine this way. I'm having a pull of electrons of carbon and chlorine going the other way. This is opposite in direction, same force opposite in direction. These two are going to cancel each other. So the net dipole is going to be equal to 0. So there is no net dipole in there. So the molecule is going to be non-polar. Okay. Let's determine the direction of polarization of each one of those. I have hydrogen, fluorine. Fluorine is more electronegative, then this is the direction of polarization. I have boron and carbon. Carbon is more electronegative, so I'm having the direction of polarization towards the carbon. Let me double check in here. I don't think that I have the electronegativity table. Yeah, I do have boron and I do have carbon, so it's included there. Okay, so where were we? Here you go. Okay, with respect to carbon and lithium, carbon is more electronegative than lithium in there. So this is the direction of polarization. And carbon and chlorine, this is going to be the direction of polarization towards the chlorine. With respect to the bond strength, um, normally sigma bonds are strong bonds. So sigma bonds, they are long bonds, they are strong bonds. Double bonds, so the more you increase the double bond character, the shorter becomes the bond. And the shorter the bond, this means that the electrons the electrons normally that are going to become closer to the s orbital, and if electrons become closer to the s orbital, this is going to add to the strength of the bond. I said here that sigma bonds are strong bonds, but they are not stronger than double bonds than the triple bonds. The double bond character shortens the bond. So here I'm having one double bond. Here I'm having three double bonds. So here I'm having two double bonds, three double bonds in there, or a triple bond. So the triple bond is going basically to shorten the length of the bond. And as the bond length is shortened, the strength of the bond is going to be higher. So it's going to take more energy from that, means that it's going to take more energy to break a triple bond than breaking a double bond, than breaking a sigma bond. You can break the sigma bond with less energy. You would need higher energy to break a triple bond. So increasing the bond strength, it has to do with hybridization. When you have an sp hybrid carbon like here, an sp hybrid carbon that is connected to a hydrogen is stronger than an sp2 hybrid carbon that is connected to a hydrogen, than an sp3 hybrid carbon that is connected to a hydrogen. This is an sp3, this is an sp2, I'm sorry, and this is an sp3. So if I am looking at the CC bond, here this is the graph for the CH bond, this is the graph for the CC bond. So the CC bond, the longer the bond, the less the double bond character in there, and the easier to break. The triple bonds are gonna be shorter in length, and they're going to be harder to break. These are the strongest bonds. Longest CC bonds, these are the weakest bonds in there. The idea here is why the sp bonds, they are the strongest. The reason why, because the sp bonds, they do have their electrons are closer to the nucleus. So as you can see, how did I know that they are closer to the nucleus? Because in their orbitals, 50% of the electrons are in the s, 50% of the electrons are in the p. So you have 50% s character, and the s orbital is the closest to the nucleus there. Here you do have actually 1/3 of the electrons in the s orbital, and here you have 1/4 of the electrons, which is 25% as an s character in the s orbital. So the more electrons are in the s orbital, the closer of course they are to the nucleus, because the s orbital is closer to the nucleus. This is the nucleus. You do have the s orbital in there. The s orbital is the closest to the nucleus with the low energy. So this is why increasing the percent s character increases the bond strength, and in that case the bond length is going to be shorter. Let's have an example over here. So let's label the shorter bond. You have a triple bond, you have a double bond. The triple bond is going to be the shortest. You have here an sp2ch bond. Okay, so here I was dealing with a carbon sp with a carbon sp, and a carbon sp2 with a carbon sp2. Here I'm dealing with a carbon sp2 hydrogen. This is what I'm dealing with here. So a carbon sp2 hydrogen and the carbon sp3 hydrogen. Which one is going to be shorter? This one is going to be shorter. This is an sp2 nitrogen that is overlapping with an sp2 carbon. So this is an sp2 compared to an sp, this is, don't forget, see, there is lone pair. Don't forget, I mentioned before, the Lewis structure doesn't show, or the skeletal structure doesn't show lone pairs, but this doesn't mean that they are not there. They are there. Please put them, because looking here, I know that this nitrogen is an sp3 hybridization. It does have 4 groups around it. So this sigma bond is the overlap between the nitrogen sp3 and the carbon sp3, because this carbon is an sp3 hybridization. So it's an overlap between carbon sp3, nitrogen sp3. This is the overlap between nitrogen sp2, carbon sp2. Of course, the sp2s are going to be shorter. Here I'm having a nitrogen sp2 hybridization, nitrogen sp2 hydrogen bond, and the nitrogen 1, 2, 3, 4, this is an sp3 hybridization. Then of course that this one is going to be basically, sorry, I circled the wrong one. So this is going to be the shorter bond over there. Okay, the last thing that we'll talk about is isomers, drawing isomers. Now, what are isomers? Isomers are, they are different molecules. They have the same molecular formula, but you can draw them differently, and every time you draw an isomer, you come up with a different structure with a different name. So the connectivity of the atoms is completely different. Like for example over here, I have these two isomers, they share the same molecular formula, but as you can see, connectivity of atoms is different. Here oxygen is between 2 carbons. This is called an ether group. This is called an ether functional group. Here I am having an OH. This is called an alcohol functional group. Okay. So I am ending up having completely different structures in there. This is called structural isomers. Another name for it is constitutional isomers. So you call it either structural or constitutional isomers. It's a way to write the same molecular formula in a different way, and every way you write, every time you write it, you get a different structure. We call those structural isomers. Structural isomers, they are Lewis structures of each other. So sometimes, so if I give you this and I ask you, draw the Lewis structure of C2H6O, one of you can draw the Lewis structure like this, another one can draw the Lewis structure like that. These two are not resonance. These two are simply structural isomers. They are constitutional isomers. You cannot go from one to the other by moving electrons. So they are not resonance in there. They are just basically structural isomers. How can you draw structural isomers? There is no one way to draw the structural isomers. We will hit on this topic again once we start functional groups in chapter number 3. We will talk about drawing structural isomers again, because you will have more idea about functional groups. But to draw structural isomers, I just came up with a way how to figure out how many structural isomers you have. The first thing is you need to identify what type of hydrocarbon you are working with. If you are working with an alkane, with an alkene, or with an alkyne. Alkane is whenever you have carbons with single bonds. Alkenes is when you have a carbon with a double bond carbon, and alkyne when you have a carbon with a triple bond carbon. They should have these molecular formulas, or in case you have a cycloalkane, they should have all of these molecular formulas. So for now, for us, I know that C4H10 is basically CnH2n plus 2, where n is the number of hydrogens. So I know that this guy over here is an alkane. This is the first step to figure out how can you draw it? What functional group are you going to use? So here I'm having an alkane. So you start with drawing the straight end chain of the alkane. And then you take one carbon and move it along the chain. If there are any cycles, you draw the cycle. So for the C4H10, you start first by drawing the end chain. What is the end chain? The end chain is basically carbons that are connected together. So go ahead and draw carbons. I'm drawing here the structural, here the skeletal. It's easier for the skeletal form. So draw the skeletal form for the alkane. This is C4H10. Count the hydrogens. Then we're going to take one carbon, move it along the chain so that we can get a different structure, not the same structure. So now if I take this carbon, and it's already on this carbon here. Let me erase that. So it's already So it's already on this carbon. It's already on this carbon. I'm just going to take it and move it to that carbon here, to this carbon there. So see that CH3? I am moving it to this carbon. So now I'm going to end up having this. So these two are constitutional isomers of each other. Forget about the name. We will talk about the name in chapter 4. C5H12, again it follows the formula of CnH2n plus 2. So I know that this is an alkane, so I don't have any double bonds in there. Start by drawing the end chain. This is 1, 2, 3, 4, and 5 carbons. Take one carbon and move it along the chain. It's already on this carbon. I'm going to go ahead and put it on this carbon now. So you're going to end up having this structure there. And then, since you have more than 4 carbons, I can take 2 carbons out and move them along the chain. So if I take those 2 carbons in here and put them on this carbon, then I'm going to end up having a branch like that. It's a carbon connected to 4 CH3s. So these are the only 3 constitutional isomers that I can come with for a formula of C5H12. Now, for C6H14, as you can see, as I increase the number of carbons, the number of constitutional isomers is going to increase. So you start first by drawing the end chain. This is again CnH2n plus 2, so it's again an alkane. Draw the end chain in there. Once you draw the end chain, take one carbon, move it along the chain. So I'm going to take this carbon, for example, put it on here. So now it's here. Let's number. This is 1, 2, 3, 4, and 5. So the CH3 is on carbon number 2. I can put the CH3 on carbon number 3. This structure is different than this one. If you end up forming the same structure, then you didn't do anything. Okay, now if I take the CH3 on carbon number 2, put it on 4, it's still the same one. It's still the same structure in there. I can take 2 carbons out. So once you finish from taking 1 carbon, moving it along the chain, take 2 carbons, move them along the chain. So I can put basically one on carbon 2 and another one on carbon 3. I can put 2 CH3s on the same carbon. So this is going to be 1, 2, 3, 4. So now I have 2 CH3s on carbon number 2. So all of those are constitutional isomers of C6H14. Just remember that the difference between isomers and resonance. Isomers should have it's different connectivity of atoms, so you have 2 different structures, completely different structures. Resonance, no. Resonance, the connectivity is the same, exactly the same. The only difference is basically the movement of electrons. So here the only difference is this side over here and this side over here, how electrons are moving between the 2 resonance structures. This is the end of chapter 1. There are assignments for chapter 1. There are assignments on Cengage Learning. I will do a small video and I will show you how to work with all of these assignments and the extra problems.